Well, good evening, doctors and practitioners. This is Dr. John Brimhall, and we have Clark Tilley running the show here, and Dr. Mark Harris, one of my best friends in the whole world, has joined us tonight. And I have to tell you, I put muzzle on him tonight, and I tell him tonight is designed to just let them know everything they're going to learn at Homecoming 2018, which is February 23rd, 24th, and 25th, and actually the 22nd we're going to be treating. Dr. Harris's schedule is already getting full, as is mine, so you better call Jason at 480-964-5198 or go to brimhall.com. Get registered for Homecoming, and if you want Dr. Harris, myself, Dr. Brett, Dr. Jesse Lehman, all the other doctors that are treating, you want to schedule an appointment for that night. Dr. Harris and I have been traveling around the country about every other month, and we have been doing stem cell seminars, not teaching you how to inject stem cells, but teaching you how to increase stem cells in the body through biological allografts and our new nutrition called OptiStem Cell. It's been exciting, and we've had a lot of MDs, DOs, nurse practitioners, etc. attending these besides chiropractors and naturopaths. And I think almost every doctor that has attended the seminars is coming to Homecoming to learn the rest of the story. We have Dr. Harris speaking 3 times during Homecoming. He's going to take this lecture and take it way beyond in how to prevent cancer and some of the treatments that are out there available. Because he is an MD and an ND and has 3 PhDs, he's granted liberties as a chiropractor I do not have in discussing such topics. But the other thing that we're really holding his feet to the fire on is the methylation. He has been researching methylation his entire life and has the audacity to remember everything he reads. If you don't know Dr. Mark, he graduated from high school when everybody else was still in diapers almost at 7, and then at 9 he finished up his 4-year college degree. It only took him that long because they didn't dare graduate him any sooner than that. Then he went on to both medical school and naturopathic school in the same city, and a lot of the classes overlap, so he was able to finish his ND, his MD, and secure 3 PhDs before his 12th birthday. Now, he's been hiding from us all of these years, and he never admitted to all of these. Finally, I have brought him out of the closet to let us know who he really is. I mean, if there's a possibility to have Einstein and Tesla and Benjamin Franklin in the same person, I think we have the privilege to have Mark on the planet at this time. I'm not sure what planet he comes from, but his knowledge and his ability to retain and to disseminate the information that he reads in 3 different languages is a godsend. It's a godsend to us, and to know him and to be able to get him to take part of his busy schedule to elaborate to us some of the things that he's researched and does in his clinical practice daily is a real pleasure. So Dr. Mark Harris, take over. We're all ears and looking forward to having everybody join us at Homecoming in February 2018. Dr. Mark.
Well, thank you, John. You humbled me with that introduction, but let's see if I can do a decent job so people are interested. Okay, so tonight we're going to talk about cancer. Cancer is one of those things when a patient hears that, really all else gets shut out from their system. They just get this immediate death thinking and go into internal turmoil. And probably all of us know someone who's had to deal with this, either from our patient load, our families, perhaps ourselves. This is the kind of thing that, because we haven't done a good job with cancer, that's why it's such a traumatic thing to think about or to hear about. So today we're going to look a little bit about what the hypotheses of cancer are and which one seems more plausible. And then once we know which one's more plausible, perhaps there's something we can do to prevent it, and if we get it, maybe to cure it. So we'll talk about some of those things. Okay, now what we all were taught with cancer, and this is in all the cancer textbooks, this was really by Robert Weinberg. He's a PhD. He was the big person who was thinking that this is all a mutation disease. And this is what we learned in medical school, that cancer goes through 6 steps. First off, they stimulate their own growth. They evade suppression. They resist apoptosis or death. They're immortal. They get their own blood supply, and they move throughout the body. And that was very much the way I was taught also when I was in school. And it seemed plausible, but some of it seemed a little odd because, we were taught that there are oncogenes and proto-oncogenes, and you get a mutation in one, and 30 years later you get cancer. And it just didn't seem terribly plausible, but we didn't have anything else that we could think about. Okay, so in 1971, we had the war on cancer declared by then President Nixon, and he asked for $100 million to launch an intensive campaign to find a cure for cancer, and then to ask for additional funding. So basically, the effort we put to put a man on the moon should make a commitment to achieve this. And that was the signing ceremony right there. And that was President Nixon, one of his, I gotta say, good idea. So how have we done on the war on cancer? Well, there was extra money. So at the time, we actually got 1.6 billion spent on cancer. But that's a drop in the bucket to what has been spent now. So to date, the National Cancer Institute, through funding, has spent $90 billion. And then there are various other nonprofits who spent an additional $2.2 billion. So you'd think, whoa, spending all that, we're probably doing pretty good on cancer. Well, let's see how good we are doing. Now, cancer, how much are we spending to treat cancer? The average cancer treatment in the US on a yearly basis, on a patient or insurance basis, is $200 billion per year. So we've spent $90 billion in research over 45 years, and now we're spending $200 billion per year. And the average patient pays about $200,000. And what do they get for their $200,000? Well, their doctor maybe gets a vacation, but cancer has become an industry. So this is one of several cancer treatment centers of America, and that's all they treat. And you probably see their advertising on television, and any cancer ward in the United States is the biggest money maker in the hospital to treat cancer. So we have to kind of ask the question, is there financial incentive to cure cancer when people are making a living on cancer, except for the people who have cancer? Okay, so now there was, this book came out in 2006, The War on Cancer, Anatomy of a Failure, a Blueprint for the Future. So basically, in any kind of measure, this has been an abject failure. But let's see what the statistics say. Okay, Mark Twain, who was notable for many things he said, talked about that figures beguile him, especially when arranging them, and he mentioned something he attributes to Disraeli, that there are three kinds of lies. There's lies, there's damn lies, and there's statistics. So the idea is that statistics can be sort of manipulated to say anything you want them to say. Now, this was especially shown in a particularly interesting study by MA and in 2015. And this was one looking at tumor shrinkage versus tumor survival. So this was in lung cancer, small cell lung cancer, and this was a fairly short-term study. Of the 49 participants, 43 of them died before the study was over. But basically, the conclusion they drew was that tumor shrinkage does not translate to a longer survival time. And it used to be that cancer statistics talked about 5 and 10-year survival, but now many of the studies talk about tumor shrinkage, so we get kind of better idea that cancer therapy is working, but it doesn't make you live any longer. Okay, let's go back to 1971 for a moment, and we had a couple different kind of videotape formats. There was the Sony Betamax, came out in 1971, and JVC came out with the VHS. Now the Betamax player was a bit of a beast, had a smaller tape though, and was generally recognized as a better player. But the VHS became the standard back then because they did a better job of promoting, and they flooded the market with the idea. So is this the case with cancer therapy, in that we have Weinberg, who is in every textbook we looked at, talking about the stages and progression of cancer? Okay, so John Yokota in Carcinogenesis, March 2000, talked about mutation theory, proto-oncogenes, oncogenes, mentioned them before, and he said it's widely accepted that cancer is attributed to the accumulation of genetic alterations in cells. So it was widely accepted because every textbook we read said that's it, and we were taught that. And the people who taught us were taught that, and the people who taught them were taught that. Then he goes on to say, however, the association between causative alterations and resulting alterations is not fully understood. And that's over the last approximately 140 years. Granted, this was in March 2000, so over the last, for when this was published, the last 132 years. But I think we've given it about time. Now, there was another hypothesis of cancer that is different than mutation. Otto Warburg won a Nobel Prize in 1931, and he's widely attributed to winning the Nobel Prize for showing that cancer cells altered the way they utilized oxygen and that they had low oxygen. But that, in fact, is not why he won the Nobel Prize. He found that in oxidative phosphorylation in the mitochondria, that there are the use of enzymes in oxidative phosphorylation, or what's called the respiratory chain. He didn't know what the enzymes were at the time, but he figured out that enzymes were making things work. And that is why he won the Nobel Prize. Now, he was nominated for a second Nobel Prize, but this is during the World War II and the Nazi era, and he wasn't allowed to be nominated in his country where he was living, so he never had the opportunity to win that second prize, even though he was nominated for it. So he also, outside of his Nobel Prize, he did other things. He wasn't just resting on his oxidative phosphorylation laurels, but he said cancer, above all other diseases, has countless secondary causes, but there's only one prime cause. The prime cause is replacement of oxygen by the fermentation of sugar. So instead of going through oxidative phosphorylation in the mitochondria, the sugar is going through glycolysis. The cancer cell is producing energy by glycolysis, which is the burning of sugar, which is not efficient, but it can occur very rapidly. Okay, so, but he, again, to his credit, he did a lot, but he could never figure out why a cell would start to metabolize sugar. Okay, so that's a picture of Dr. Warburg. So the enzymes he was talking about are the well-known enzymes now we have in the mitochondrial intermembrane space, in the inner mitochondrial membrane. So we have complex 1, NADH dehydrogenase, 2-succinate dehydrogenase, complex 3, cytochrome B and C, cytochrome C oxidase, and ATP synthase. Now, just a little bit of an aside with ATP synthase, because it's perhaps interesting. So that's depicted as a little kind of drum, a little round drum. So to use ATP, you strip off a phosphate, and then you have to replenish a phosphate. And that little drum rotates. As it rotates, it replaces the phosphates as they're used up. Now, at rest, those things turn at 3,000 RPMs. And we have approximately 10,000 of those per mitochondrion. As we begin to exercise, they churn out 20,000 RPMs and 10,000 per mitochondrion. Just a little bit of I think, interesting. Okay, so let's look again at Betamax versus VHS. Mutation theory, 120 years. Metabolism theory was proposed in the mid-1930s, about 80 years of that. So do we have a mitochondria that is happy? versus one that is toxic? Or do we have a mutation in the DNA? Well, what Warburg also discovered, low oxygen, when intracellular oxygen drops by 35%, cells become obligate sugar metabolizers. There's not enough oxygen to run oxidative phosphorylation. So cells become obligate to their sugar in glycolysis. But why would cellular oxygen drop? What causes it to drop? Is this a mutation in the mitochondria? Well, that's when Weinberg, the fellow who had the 6 items that is in all our textbooks, when he heard this theory, his idea was, well, there's a mutation in the mitochondria. So his hypothesis was still correct. But perhaps this is a case of using words to fit your hypothesis instead of changing your hypothesis. Because my own thinking is that we're all entitled to our own opinion, but we're not entitled to our own facts. Okay, so what happened next? There's no conclusive research on human subjects to prove that sugar makes cancerous cells grow and metastasize. Well, who said that? That was the Cancer Treatment Cell Centers of America, the very same people we saw who are among the recipients of the $200 billion a year that's being spent on this. Oh, and let me just pause for a moment. If there's any questions that come up during this, please feel free to type them into your question box and we'll answer them at the conclusion of the comments. Okay, well, Cancer Treatment Center says there's no evidence that cancer metabolizes sugar. Well, let's look a little bit at some of that data. Okay, now, this was from the American Diabetes Association and the American Cancer Society, and they asked them the same question. They said, we aren't sure. But even so, lifestyle cuts cancer risk. And then they went on at the end, we should prevent diabetes, then we can prevent some cancers. And those who do have diabetes, it should be controlled as much as possible through a healthy lifestyle. And that diabetes doubles the risk of liver, pancreas, endometrial cancer, and increases the risk of colorectal, breast, and bladder cancer by 20 to 50%. And that was from the American Diabetes Association, the American Cancer Society. And they said that, but what's the data say? Oh, by the way, that came off of WebMD. All right, now let's look at one of the technologies that is used to detect cancer, and that's a PET scan, positron emission tomography. Now, they got one of these in a hospital in Anchorage, but they had to import the isotopes. You need nuclear isotopes to run these things. They had to get the isotopes out of Seattle. So this fella had this idea. Basically, the instrument they used to generate the isotopes, or a cyclotron, he bought a used one from Columbia University and set it up in his garage and started generating nuclear isotopes. He thought he'd sell them to the hospital and make a fortune. Now, for most places where the cyclotrons are placed, they have foot-thick cement walls and lead lining it. Well, the neighbors were justifiably upset, and the Anchorage City Council quickly passed an ordinance that you can't have cyclotrons in residential neighborhoods. Okay, now the chemical they use to light up the cancer cells is 2-deoxy-2-18F-fluoro-D-glucose, because the cancer cells metabolize the glucose and they can see active cancer cells. So first thing about 2-deoxy-2-fluoro-D-glucose, the oxygen is taken out of them, just what cancer cells love. And the fluoro part is fluoride. The reason it's used is because it's highly reactive with things, so you can bind it to glucose, but it's also highly toxic to everything. So you're taking a very toxic thing, you're depriving it of oxygen, and you're putting glucose in to light up a cancer cell. But you're also feeding it. Okay, but do we have enough evidence that glucose is part of cancer? Okay, this is from Google Scholar. And if you're not familiar with Google Scholar, it's similar to PubMed, but it's perhaps more comprehensive. So when you type in glucose and cancer, as I did on that page, you see there are 3,050,000 studies on glucose and cancer. So Granted, I haven't read all of them, but I did read a lot of them. And if you read a lot of these studies, what it looks to be is that 95% of cancers utilize sugar as a fuel. And the 5% that don't never grow fast enough to ever cause a problem. So for all intents and purposes, cancer cells are utilizing sugar as a fuel, just as Warburg said they did. So sugar is part of it, but what about iron? Well, this was an interesting study on iron miners, and they were followed for 5 years. 40 of them died, 13 had lung cancer. It was 3 times the number that was expected amongst the normal population. So then in a couple other studies, it shows basically high iron stores could promote development of cancer. And this was not just the miners at this point, so a couple other studies that are showing that. So what's happening with iron? That. No, not Iron Man. Okay, but we're going to get back to iron in just a moment because there's an emotional component to cancer as well. Reich Hammer was a medical doctor in Germany. He was in practice in Rome. His son came to visit and was accidentally shot at age 17 and died. So he described what he called Dirk-Hammer syndrome. What this means is that when you have a large emotional stress that you are unprepared for, and at the time of the stress, you do not have any intellectual capacity to deal with it. Because within 1 year of his son being killed, Dr. Hammer developed testicular cancer. So we talked about diseases progressing in 2 stages. First being conflict active phase, the emotional distress or Dirk-Hammer syndrome, where you typically lose your appetite and have insomnia, where there's a healing phase that's marked by fatigue, headaches, inflammation, infections, and pain. And Hammer taught his techniques. It got to be very detailed. It actually became something of a very large procedure. I studied with him in 1993. He at the time was living in Spain, and I went over there. It's one of the last times he taught, and he died this past July, on July 2nd. And he did some, he would just really, for most people, treat the emotions, and he had a very strong success rate curing the cancer. All right, so, but we're going to go back to oxygen now, because, well, how do we get oxygen to our cells? Well, of course, the first thing we do is we breathe, and oxygen goes to our lungs. So we have to look at lung health. On the left, you see lungs from cadavers. On the left, you see some pink, dead, but good-looking lungs. The right are lungs from a smoker, and they'll often look very much the same in a miner. And first off, do you get enough oxygen into your lungs? And the second thing, are you a chest breather or are you an abdominal breather? And most of us learn to breathe into our chest in junior high school when both boys and girls want to look chesty because we're starting to get attracted to the opposite sex. Now, thank goodness that smoking is going down, but then do we get enough oxygen, or are we in a shock breathing pattern, not getting enough oxygen, breathing too shallow? Okay, then we get from our lungs the breath that's going to go to our heart. And how good's your heart doing? Do you have a nice looking heart, or do you have a fatty heart? Is your heart pumping efficiently? So oxygen has to get into the lungs, then go to the heart for its next step into the arteries. And do they have clear passage to the arteries? Is there some kind of atherosclerotic plaque? Is there some kind of blockage to the flow of oxygen? Or is there some kind of dehydration that will diminish the thickness of the plasma, so hard to get the blood through it? And how about the blood cells themselves? So a healthy blood cell, when it gets down to the capillary level, will squeeze through 1 cell at a time. So what's making up the cellular membrane becomes crucial to the functioning of the red blood cell, and that's primarily determined by the essential fatty acids. And there are good essential fatty acids and there are bad ones. So we'll talk more about that when I have more time to speak to you at homecoming. Then various things can cause a rouleau where you can't get enough oxygen, and then you can get crenated cells also. And this can be from infection, this can be from stress, and then we have lower carrying capacity of oxygen to our cells. and different ability of these cells to give up the oxygen. So we have to get oxygen to our mitochondria. If we don't, we're at higher risk of cancer. Okay, so what happens with blood? You can have intestinal problems, you can have too much protein, continued intestinal problems, irritable bowel or colitis, all curable, but have to figure out why do they have it. Inflammatory foods, things like sugar, things like wheat, things like grains, food sensitivities, dysbiosis, degenerative diseases, stress, coffee, sugar, and zeta potential can be off. And zeta potential is the electrical activity in the cell. Cells should have about minus 70 millivolts. If that gets off, then the calcium, potassium, salt balance gets screwed up. And then you can have anemia from either iron deficiency or B12 deficiency, which is far more common. Because one of the big raps on a vegan diet is you don't get any B12 in a vegan diet. Well, you get plenty in animal products. It just, you can't absorb it. Because after age 35, we get low on pepsin, then we can't absorb that B12. So really B12 becomes crucially important to health, but the form of B12 makes a difference. Okay, and then as we get older, here you see a 20-year-old woman, there a 20-year-old man, 80-year-old woman, 80-year-old man. So what's happening as we get older? Perhaps we're losing our vision, although the 80-year-old man still seems to be able to see very well. But the appearance is different. Why do we change this way? Okay, mitochondria, and this is clear in the literature, starting at age 20, they drop by 10% per decade. So as we age, oxygen enters the mitochondria, but we don't use it as efficiently. We make less ATP, which is why we begin to get fatigued as we get older. But because the oxygen is still entering the mitochondria, we make more oxidative stress. And that's what ages us. And of course, the oxygen level goes down because we're not utilizing the oxygen as efficiently, is why it becomes oxidative stress instead of ATP. So what happens inside the mitochondria, you've got the inner mitochondrial membrane I mentioned earlier with the complexes. And then as the oxygen is not used to make ATP, it goes to make this O-no molecule called peroxynitrite. And then if we make less superoxide dismutase, and there are several types of superoxide dismutase, this one requiring manganese. And then if you make this chemical, then you're causing oxidative damage inside the cell and in every cell inside your body. Now this is also the chemical that's going to screw up your methylation pathways, which happen to a little bit of an argument in the biological community. Some people say it happens 1 billion times a second. Some people say 2 billion times a second. I think it's a moot point. It's a lot. So basically anything that screws up the oxygen utilization in the cell, and that can be age, that can be heavy metals, that can be chemicals, that can be stress, then the oxygen is not utilized, cellular oxygen drops, and reactive oxygen species increase. So what are we doing for cancer in our standard therapy? Well, the three things that are probably been offered to anyone who has cancer are surgery, chemotherapy, and radiation. Some people call this cut, poison, and burn, and I think that's a fair way to talk about it. Well, then we look at cancer statistics, as we promised we would. So there's a fairly arbitrary hallmark of a 5-year survival. But if you compare that to other people of the same age without cancer, 5-year survival becomes a mystery as why it's called a 5-year survival. Okay, so what we found, if you actually look at the actual data, that we have somewhat of success on 11 out of 200 types of cancer. And if you look at the actual numbers for 5 years, that results in a 2% cure rate. This is after the 1971 war on cancer, and now 45 years later. So it's estimated worldwide that 1 patient per minute is diagnosed with cancer and dies of cancer. And if we had a terrorist that was killing 1 person per minute, we would be endless in our search, no cost spared, to find the perpetrator of that death. Yet, we're still looking for the mutation theory of cancer, or even Weinberg, who came up with it, or was the one that wrote it down, is even saying now there's very little data to support it. So what about oxygen? If it's an oxygen problem, can't we just give people oxygen? Well, Warburg tried that. But really by the time the cell starts using the glucose, it's a case of closing the barn door after the horse has left. Okay, so how do we approach cancer from a preventive standpoint? We want to restrict sugar in our diet. This is any added sugar. This is grains. This is the sweet fruits, bananas, strawberries. This is the kind of things that we want to limit, whether we can handle sugar well or not. Because if you can prevent cancer with a low sugar diet, you can prevent a lot of other chronic diseases as well. So a ketogenic diet is one where iron is a part of where fat comprises 70 to 80% of the diet, protein about 10%, and non-fiber carbohydrates about 10%. We want to eat anti-inflammatory, and that's mostly by eating vegetables. And we want to have low heme iron, because the iron can also create another reactive oxygen species called the oxygen radical. So heme iron, as opposed to non-heme iron is the iron that is in animal protein. Now, animal protein is not all bad, but the amount makes a difference. And over time, we tend to build up iron stores in the body, and I like to measure ferritin in my patients, and I want ferritin levels to be between 60 and 80, and really no higher than that, or you're starting to get more oxidative load in your body, and you're starting to decrease mitochondrial function and decrease iron stores. Okay, now there's another thing that I like to do for my patients that has probably the biggest benefit in a short-term basis, and that is a therapeutic water fast. Now, there's a couple kinds of fasting, and when you say fasting, people often confuse fasting with starvation. So here's two kinds of starvation. The fella on the right, the more corpulent of the two, is eating a nutrient deplete diet where he is starving himself of nutrients, although he is robust in his appearance. The fella on the left has lost all his muscle mass, and muscles, of course, are made of protein, so he is starving. So both of them are starving. Now we got this fellow who's also starving. When I saw this, it kind of broke my heart. I'm a dog lover, and for those of you who are dog lovers as well, I want to show you this. There's a wee bit of a happy ending here, so watch a short 45-second video. Okay, so, and my kudos to Eduardo, who brought that beautiful animal back to health. And even notice in starvation, the wagging tail. We could probably do well to emulate the love that dogs can provide. Okay, so fasting, when you're actually fasting water only, if you are doing a juice fast, you're having a reduced calorie diet. That is not fasting. So 1 to 2 days of water only fasting, you're going to burn up all your glucose. So cancer cells do not have anything to eat. It's going to take 2 to 3 days, depending on gender. Women do a little bit faster than men. You're going to start to make ketones. And cancer cells cannot use ketones, but they can use something else if you're not burning ketones, if there are only ketones in the body. And we'll talk about that as we have more time at homecoming. And then you're burning fat for fuel. Now, this is one method that you do not want to burn fat for fuel. Okay, now there's something else that goes on in a cancer cell, is we have what we call our cytoskeleton, This is from the most basic of organisms called the archaea, which predate bacteria, to our own cells. So you see the ribosomes and you see the microfilaments between the cells and the microtubules. We call that the cytoskeleton. But this is different in a cancer cell. So in a cancer cell, the cytoskeleton protrudes and has adhesion molecules all throughout the cell, and this effectively omits other things from entering the cancer cell. So knowing this happens, there's something we have to do to kind of trick the cancer cells into admitting nutrients and deprive them of the nutrients they want. So, because we have to get around the cytoskeleton. Okay, now, John Beard, he died in 1923, and this book came out in 1911. He was using injectable enzymes. His thinking was that cancer was a problem of enzymes produced by the pancreas that became problematic, and then to use the enzymes to cure cancer. Well, he was curing cancer back in his time, and it got kind of forgotten until William Donald Kelly, William, not William, typo, my apologies. He was doing the enzymes orally, and he retired in 1986 under, he was kind of ostracized and harassed because he had the audacity to cure cancer. Okay, now, there was someone who was hired to discredit Kelly. His name was Nicholas Gonzalez. And he went in to discredit Kelly and spend a bit of time with him under false pretense, but was so unbelievably impressed with Kelly himself and with the results he was getting that he himself took over Kelly's practice when he stopped doing it. So he died in 2015 under some mysterious circumstances, as many doctors did around that time, upwards of 60 doctors who were doing things that were outside mainstream. So he wrote 2 books on cancer, volumes 1 and 2, that are still available. And he basically was using the Kelly protocol, using digestive enzymes in pretty high amounts to cure his patients of cancer. But this ended up being a very expensive therapy, but nothing at all compared to approximately $200,000 people would spend going through chemotherapy, radiation, or surgery. Okay, now the other thing cancer cells do is they, when a tumor is very small, it doesn't have a blood supply, so it can't get very large at all. But then the tumor will start secreting angiogenic factors. These are some proteins and hormone-like substances, and then that will start to recruit blood cells into the tumor. Then the tumor has a blood supply, and now it can grow larger. And then it can spread through the blood vessels itself, but there's some other way it spreads. We'll talk about that more at homecoming. Now, some of the thinking is that they like to interrupt the flow of blood because then this will regress to a small tumor. Well, that is not my thinking initially, because once you get a small tumor, it can do this again and become that again. And if you want to get some nutrients to a cancer cell to kill it, you want it to have a blood supply. So really, once you can kill cancer cells, the blood supply will go away of its own accord. So really the idea here is not you want to starve the cancer cell from a blood perspective, but starve it from a nutrient perspective, and then it will shrink, and then your own immune system can take care of it. Okay, so we're going to look at one other interesting study here. Now this was the Philosophical Transactions of the Royal Society. Perhaps only the British could have a journal of that name. So this one was published in 2014 by Switek, Jones, and Harris, not me, a different Harris. I have published some stuff, but that wasn't one of mine. So what they were talking about was the presence of areas with low oxygen tensions associated with increased metastasis and poor patient survival, giving the rise to the notion that hypoxia is the hallmark of malignant cancer. So once again, they're kind of proving Warburg's hypothesis. This is a problem of oxygen and metabolism in the mitochondria. But we still don't know why, or do we? Well, in summary, cancer is metabolic. We kind of know that now. It really isn't a mutation disease. It's not caused by that. There's been enough evidence to prove it. We understand enough to think about a cure. And what would I do if a family member had cancer? Because we've kind of learned enough about cancer to come up with treatment for cancer. But if we treat cancer, we tend to go the way of Dr. Gonzalez. But if my own family member had cancer, what would I do for them? Well, I'm going to talk about some of those things at Brimhall Homecoming in 2018, the third weekend in February, and I hope to see you all there with a couple of additional talks I'll be doing about methylation and about permanent pain cure. So if we have questions at this point, please type them in, and I or Clark will be able to see them, and I'd be happy to answer them to the best of my ability. So let's give a couple minutes for that. Okay, we don't see any questions coming forth. But what I'll kind of close in saying, when a person has cancer, it does not take away their soul. It does not take away their friends. It does not take away their person. It doesn't take away their being. It's a trauma of emotional proportion that is almost unknown anywhere else in life. But cancer is not a death sentence. Okay, if we have no questions then, I think perhaps we'll let you go for the evening. I thank you so much for joining me this evening. I hope you've learned something from it, and then if you have questions that you think of between now and homecoming, feel free to bring them to my attention then. It'll be one of my 3 lectures, and I hope you'll to see you there, and I hope you'll find them very informational and things that you can do for you, your patients, and your family.